Yeah, so it's a pleasure to tell you a bit about some recent research that I've been doing with a couple of people here in Exeter on fast and slow domino regimes for transient escapes and networks. And it's a pleasure to present this to the Network Frontier talk. Oh dear, things are not working very well. Okay, so I'm going to talk a little bit about the idea of cascades of escapes, cascades of transient escapes. I'll spend some time talking about a two-node example, which is bidirectional coupled, before moving on to a probably more interesting case where we consider a chain of three coupled nodes. We'll then talk a bit about bistable oscillators, some generalizations, and then a bit of discussion. So, what is this about? Well, we've been thinking about the type of phenomena where a failure or a tipping point or some critical transition in one system has a knock-on effect on another system. So there are various places in science and economics where this appears. So, for example, one typical question in long-term climate science is to try and understand how the tipping of one element within the climate system could affect another one. For example, if the Atlantic meridional overturning circulation stops, how does that affect the Indian monsoon? Or there are a variety of systems one could look at. Another question in finance is, if you have bankruptcy of one financial institution or a default, how does it affect others? There's been work on that, looking, for example, at network models of contagion in financial systems. And finally, how does epilepsy spread during seizures? So it's known that epilepsy is associated with highly synchronous behavior in certain regions of the brain. You can measure that in EEG. How does that spread during the propagation of a seizure? And this is joint work with Jen Creaser and Krasitsaneva Atanasova. So to start off with, let's consider dynamics of a simple system, a one-dimensional system that has two attractors. So the idea is you have a potential which has like a shallow well and a deep well. And we can start the state either at the shallow well or at the deep well. So we call the shallow well the quiescent attractor, and the deep well is the active attractor. And so the sort of question we're considering is we start a number of systems all at the quiescent attractor and then consider what happens under the influence of perturbations. There could be noise perturbations, or they could be coupling to other systems. And I should say that this is very much inspired by work of Berglund, Fernandez and Gentz from 2007, where they looked at chains of such systems that were symmetric. So you had two attractors of similar depth. So the particular system that we've considered is a set of coupled stochastic differential equations of the form shown here, where you have the dynamics of the individual nodes is represented by the F, and then you have some simple diffusive coupling term where you have a network of connections that is characterized by this set Ni. So Ni is the set of neighbors that provide inputs to node I. Beta is a coupling strength, and then we have some additional additive noise terms, which for simplicity we'll assume are independent Wiener processes. So if we now start this network in a situation where all nodes are in this quiescent attracting state, for the simple case of uncoupled systems, we know that the escapes will be independent of location. This means that we have a number of identically distributed independent processes, and cascade doesn't really happen other than through random processes. So there's no dependence of one escape on the other. So the interesting question is, how the statistics, and in particular the dependence of the escape and the orders of the escape, how does this change as you change the coupling strength, beta, and the network structure, which you characterize by the Ni. And I should say that there's an extensive literature in this area which has been looking at bistable elements in the influence of noise, but we haven't found really specifically address this question about how do transient escapes spread throughout the system. So you can think of this as like a domino effect, where the toppling of one domino affects other dominoes in some way. So a particular two-node example we consider here, bidirectional coupling, and equation 3 shows the system. So for any beta, because of the form of the coupling, we will have states where both systems are in the quiescent state or both in the active state. And of course there is a saddle somewhere in the middle, which is provides a separatrix between the two different basins of attraction. So that's in the noise-free case, alpha is 0. If we consider the case where beta goes to 0, there are a number of additional equilibria which are sort of continue from the case of beta equals 0. So in particular, we've got the cases where one has escaped, say the first one is active and the second one is still quiescent. Similarly, the other way around, all cases where one is active and the other is on the saddle. So for this system and the F I provided previously, you can nicely characterize where the latter equilibria disappear and are replaced only by the first set of equilibria. So there are saddle node bifurcations that depend on beta. So this is in the limit as alpha goes to 0. So in particular, for small values of nu, which means we have a high degree of asymmetry, the first bifurcation is a saddle node bifurcation, and then we have a pitchfork bifurcation. So this shows the bifurcation diagram where we're changing the coupling strength beta. This shows one of the variables, x, and you can see we start off with a total of 9 equilibria here, 4 of which are stable, and this continues up to the saddle node bifurcation. Beyond that point, there are only 2 attractors. We have the quiescent state where both are quiescent and case where both are active. But notice that there are bifurcations of the basin boundary, as we will see, between beta 1 and beta 2. So how do we characterize something like the cascade of dominoes? So if we start off with, for example, one of the nodes, let's say the ith node in the quiescent state, and we'll pick a threshold that is somewhere just after you've tipped, you can characterize the first escape time of node I. That's a random variable, which is the first time when you exceed this threshold. And then for any realization, for any given initial condition and realization of the noise, you will have an escape sequence where you can find a permutation of 1 to n such that tau si is less than tau sj for any I less than j. So this means that we can characterize the sequences of escapes, or the sequences in which the cascade happens, as a random permutation where the probability, at least in the case of uncoupled, beta equals 0, is all sequences are equally likely. We can also look at the timing of the that in general that will be a distribution. So we can look at the time of the ith escape, we can look at the time between the escapes, and we can look at the means. But of course, as I said, these are distributions, so they may not be just memoryless exponential distributions. They can have some more interesting behavior. So certainly in the case where nu is small, and beta is 0, you can approximate the mean time of escape using Kramer's type formula, where you characterize well, it's an exponential in the height of the potential that you need to exceed. However, on increasing beta, certainly numerical evidence says that there are some quite subtle changes in the orders in which escapes happen, and also in the timing, the distributions of the timing. But in general, there seem to be three regimes. We have a weak coupled regime, small beta, where the quiescent states are perturbed but not destroyed, and basically you get something that is just a modification of the rates you would get for the uncoupled case. For the strong coupled regime, this is a synchronized case regime where if one of the dominoes topple, then the other one actually topples at the same time. So we call this a fast domino effect. The most interesting regime is actually in the middle, where you have, for example, one domino topples, then the other one is actually committed to toppling. It will topple, but there could be some delay, which is essentially a deterministic response, and we call this a slow domino. So we can characterize this by looking at the potential in this two bidirectionally coupled system case. We get a two-dimensional potential, and we can understand the behavior from the behavior of the trajectories within that landscape. So the top left shows we start a trajectory somewhere in the bottom left where they're both quiescent, and you escape first, the second one escapes, and then the first one escapes. As we increase beta, so for example in the bottom left we have a slow domino case where escape from this equilibrium, the stable equilibrium, will take us to where a saddle node has just been. We will linger there for a while before moving on. So this is a slow domino, whereas for the fast domino, basically we are restricted to the synchronized subspace. So one of the implications of these three regimes is that we'll have different asymptotic formulae for how the mean escape times behave. In particular, if we look at the mean escape time to go from none escaped to two escaped, the formula for that will change in some subtle way, corresponding to how what the intermediate states are. And then just to talk a little bit about the n=3 case, where we have three bistable systems coupled in a row. So in this case we have 3 is coupled to 2 and 2 is coupled to 1. If we look at the bifurcation diagram for this, we'll find in fact the intermediate regime splits further. So we get between beta 1 and beta 2, we get a regime where some of the intermediate escape states are still stable, but others are not. And we've still got strongly synchronized fast domino regime. Okay. And then just to present some numerics, really, there's more details in the paper. If you look at the typical distributions of escape, so this is time of escape by the number of the nodes, you can see actually for the cases for beta = 0, beta is 0.1, or beta is 0.4, there's not really much change. But what there is what there are very significant differences in is the conditional distributions of escape time. So the distribution of the first escape, the second escape, and the third escape, and also the probability of different sequences being seen. That can change quite dramatically as you increase beta. You can characterize that using coefficient of variation, and then I'll just very briefly mention an application of this to coupled bistable, where we've been examining these effects in a case where we have, rather than just simple equilibria, we have bistability between an equilibrium and a periodic orbit. and we can similarly find different regimes of escape corresponding to whether there's an intermediate temporary states that the system visits, or whether it's strongly synchronized. Okay, so just to very briefly sum up, the main message is that there can be qualitatively different escapes depending on coupling strength and on network structure, and these can be seen as an emergent behavior of the system, and we think it's very interesting to understand features of this emergent behavior. So finally, thanks for listening, and I've put 2 references up there, and thanks to EPSRC and EU critics for their support. Thank you.